is going to be the limit. So, if we look at something like x squared minus 9, I'm going to pull this up. We're going to kind of link this to what we've been doing with the graphs. So I'm going to put this into Desmos. You don't have to get yours out to do it. We just want to look at it real quick. X squared minus 9 is just a parabola. We are looking at where x equals 5, which is right here on this graph. And as we approach from the left, we go closer and closer and closer to that point right there. And as we approach from the right, we also go closer and closer to that point. And it's a closed dot, it's filled in, so we're approaching this point, and its y value is 16. Mathematically, algebraically, what is the way that we can find a y value if we know the x value? Just plug it in, right? So in this case, what we need to do is we need to take 5, we need to plug it in for the x, or any of the x's that are in the problem. So we will have 5 squared minus 9, which is 25 minus 9, which is the 16 that we were seeing on the graph. Okay, so this is called direct substitution. If you can plug your value into your equation and it gives you a valid answer, that is your answer. So this is the super easiest form of algebraic limits, just plugging in the number. If we're doing example 2, we're just plugging that 2 in right there for the x. So we would have 1 over 2 plus 2, which would give us 1/4. And that would be the answer. So if you can plug the number in and you get a value, that value is your answer. However, if we look at example 3, most of the limits I'm going to ask you are not going to be direct substitution, because those are not the interesting parts of the graph, the parts where we would care about that limit. So here is one way that one thing that you are going to see. You may see something that happens like this, where we do 2 minus 2 and we get 1 over 0. 1 over 0 is undefined. Okay, so if we get any number besides 0, over 0, then this is going to be a guaranteed does not exist. Usually this is going to happen at a vertical asymptote somewhere on the graph. And if you think about the graph of 1 over x minus 2, you got the x minus 2 in the bottom, it doesn't cancel out with the top, you have a vertical asymptote at that point. Now, if you have any number besides 0 divided by 0, that is automatically a does not exist. You don't have to do anything else for that problem. Your answer is does not exist. But here's what we're going to see most often. Direct substitution is going to fail whenever you get 0 over 0. So 0 over 0, this is called indeterminate. Or sometimes you'll see indeterminate form. And indeterminate means just like what it sounds like. You cannot determine anything from this value. Okay? It does not necessarily tell you that the limit does not exist. It only tells you that you can't tell at this point. Okay? So it's different than getting 1 over 0 or 7 over 0 or 28 over 0, right? Those all mean that you do not have a limit at that point, probably because of a vertical asymptote, but not always. 0 over 0, you may still have a limit that exists. So for example, right here, we've got the limit as x approaches 2 of x minus 2 over x squared minus 3x plus 2. If we try to plug in 2, we get 2 minus 2 over 2 squared minus 3 times 2 plus 2, which is going to be 0 over 4 minus 6 plus 2, and 4 minus 6 plus 2 is also 0. I'm going to put a little star right here. Not mathematically correct. Nothing can equal 0 over 0. Technically, I should not be letting you write equals 0 over 0. It is a big thing on the calculus exam whenever we do L'Hopital's rule that you can't write something equals 0 over 0. The way that you can write it is that you write it is of the indeterminate form, 0 over 0, instead of putting that equals 0 over 0. Technically, nothing can equal that, so it is technically mathematically incorrect. Oh, I didn't put incorrect, did I? All right, I'll put not mathematically correct. Okay, we're all right. Not mathematically correct to write this. But at this point in your math career, I don't care if you write it, it's fine. Whenever, just know that, like, whenever we get to L'Hopital's rule, in calculus, whenever we're there, I am going to say you can't do this anymore. So I like to give that warning, so you know that's coming up. But if you put equals 0 over 0, it's okay. But that is not ever going to be your answer. Okay? Never should you put your answer as 0 over 0 and circle it. Okay? 0 over 0, what it means is it means keep going. It means there might be a limit, there might not, but you can't tell right now. You got to do something else. So, let's talk about what the something else is, what you're going to do if you're trying to figure that out. So, the first strategy that we're going to talk about is factoring and canceling. Okay? So, every time you should plug in the number because it might be direct substitution. You can do this in your head. You don't necessarily have to write it down, but you should plug in the number. We just did because this is the same problem that we had on example 4. So we have already checked. We're getting 0 over 0. So what we are going to do is we are going to factor the top and bottom here. So until you have plugged in the number, you cannot drop limit notation. So you want to keep the limit notation. You've got x minus 2 over x here, and then we would have a minus 2 right here and a minus 1. And so your x minus 2's can cancel, and you will have the limit as x approaches 2 of 1 over x minus 1. As long as you still have an x in your expression, you have to keep your limit notation. But once you cancel something, you can probably plug the number in most cases anyway. So if we take that 2 right there and plug it in for our x, we will get 1 over 2 minus 1, which will give us 1. So our limit at this point is 1. If we switch over to Desmos real quick just to look at what we're seeing here. If we look at x equals 2, it looks like it's solid right there. But when you're clicking on that green graph, right there, there we go, right there, it is undefined. So you got a hole in the graph, but the y value that you approach is 1 for that. Okay, this guarantees that that's the case, whereas numerically or the graph just supports it's the case. Okay, questions on that? All right, let's try a couple more. Okay, again, for these, I'm not going to be terribly hard on you for this unit on notation, because you will take this test on Canvas, and you're going to be selecting multiple choice or typing box answers. So I'm not going to be looking at your work really close, but in calculus I will. So just know that if you're signed up for that, that's coming. So we do not drop limit notation yet. Limit as x approaches -3. Factor the top, x plus 2, x plus 3. Oh, what did I forget to do? I didn't check to see if it gives me 0 over 0. Does it give me 0 over 0? It does. So I should check that every time. In fact, it's one of the most missed questions that I have on this test is one that is a fraction and looks like it should factor, but is actually just direct substitution. Students miss that one all the time because they forget to check direct substitution. So this is going to be the limit as x approaches -3 of x plus 2. And then we just have to plug in our number. -3 plus 2 is going to give us -1. Okay, questions on that one? All right, next one. Can we factor it like it is right now? Actually, first, does it give us 0 over 0? Okay, bottom definitely gives me 0. -6 plus 3 is going to be -3 squared. You get 9. 9 minus 9 is 0. So we get 0 over 0 for this. We want to check that every time. This does give you 0 over 0, so we're going to have to do something else. Can we factor it like it is? What do you mean when you say pull it apart? You can do that. You could write x plus 3 times x plus 3 minus 9. What would you have to do after that? Because nothing will cancel right there. Even if you had x plus 3 on the bottom, it would not cancel because of the minus 9 on the end. Okay, so we could multiply it, distribute it here, so or square double square for this. So if we do that, we'll have the limit as x approaches -6 of x squared plus 6x plus 9 minus 9. And that's going to be the limit as x approaches -6 of x squared plus 6x over x plus 6. Okay, what do we do after that? Because we've kind of worked on this, but we're still going to get 0 over 0 if we plug in -6 right here. We haven't really like canceled anything out except for maybe I guess those 9s right there. So we still got to keep going. What can we try now? Okay, we're going to factor the top. How could we factor it? You can do it that way. I don't love it. I would just take an x out. X plus 6, x plus 0 is technically correct as well. But I would just write it as x times x plus 6. And then you got the x plus 6 on the bottom. And now your x plus 6's can cancel. So you got the limit as x approaches -6 of x, which is just going to be -6 as your answer. Questions? All right, what about 7? Work on 7 there, see what you can do. Alright, I see lots of you doing the right thing on that. What should you do first on number 7? What should you always do first on every problem? Plug the number in, right? Because after we've done a lot of these problems, you're not going to see a lot of these like this. Most of them are going to factor. And so lots of students fly in on factoring right away on this. But you need to plug in that 2. So you'll have 2 squared minus 4 times 2 plus 3 over 2 plus 3. And so 4 minus 8 plus 3 over 5 is going to be, let's see, negative 4 plus 5 is negative 1/5. So you should get negative 1/5 as your answer. So no factoring or canceling on that one. Okay, questions? Okay, so one strategy that you have is to factor and cancel. Typically, if you're getting 0 over 0 and you see something like that will factor, it's probably the route you want to take. Let's look at some other types of problems you're going to run into. Okay, this one has a square root in it. And if you plug in 1, square root of 1 is 1, minus 1 will give you 0 in top, 0 in bottom. You're getting 0 over 0 here. So another option is to rationalize. It can be numerator or denominator. We worked on rationalizing denominators earlier, like if we had 5 over 1 plus the square root of 2. How do we get rid of that 1 over 1 plus square root of 2 in the denominator? Not the reciprocal. It has a different word, different name. What is it? What would it be for this one? What would we multiply by to get rid of that root in the bottom? 1 minus the square root of 2. It's called the conjugate. So you would multiply on top and bottom by the conjugate, right? And so for this particular problem, you would get 5 times 1 minus square root of 2. And on the bottom, yeah, this is just an example to remind you about rationalizing. We would get 1 minus the square root of 2 plus the square root of 2. Those cancel each other out. Minus 2. So you would have basically, it's just going to give you a negative 1. So it would be like negative 5 times 1 minus square root of 2. All right. So to get rid of the square root, you multiply by the conjugate. Now with limits, what you might see is the square root might be in the top or the bottom. For rationalizing numbers here, it was always the bottom we were concerned about because that's just standard for like mathematical practice. But for these, it might be top or bottom. It doesn't matter where it's at. But a lot of times rationalizing will help get something moved around where something will cancel, and then you will be able to find the limit here. So what we're going to do for this one is we're going to multiply by the conjugate. So we're going to multiply by square root of x plus 1 on top and bottom. So in the numerator, you want to multiply this together. So square root of x times square root of x is just x. You will get a positive square root of x and a negative square root of x. They will cancel each other out. I'm not going to write them because they cancel each other out. And then you'll have a minus 1. On the denominator, don't multiply. Because we want something to cancel, and you can see right here that if we don't multiply it back together, the x minus 1s can cancel. So we would have the limit as x approaches 1 of 1 over square root of x plus 1. And then at this point, all we need to do is take that 1, plug it in for our x. So 1 over square root of 1 plus 1 is going to give us 1/2. There. Okay, questions? Typically, once you rationalize, there will be something that will cancel with the other side. And in general, if you ever cancel anything top and bottom, there's a good chance you can plug in your number after that, unless it's a extra complicated problem. All right, let's look at this one. This one's a little bit more complicated than the last. We got the limit as x approaches 5 of the square root of x minus 1 minus 2 over x minus 5. If you plug in 5, you get square root of 4, which is 2, minus 2 gives you a 0 in the top. 5 minus 5 will give you 0 in the bottom. So 0 over 0 for this, we're going to have to try to rationalize. What is the conjugate of square root of x minus 1 minus 2? Nope. It's square root of x minus 1 plus 2. So only the sign in between changes. But Gabby did exactly what most people do incorrectly, which I don't know that we have dealt with a problem like this, so very understandable why you would do that. Whatever's under the square root, you do not change that sign. It is only the sign in between that changes. And the reason that that's the case is because we want to create a difference of squares. We need it to be, when we multiply the two square roots together, that we're multiplying the same thing there. So we've got limit as x approaches 5. We'll hold on to that limit notation. So square root of x minus 1 times square root of x minus 1 is x minus 1. Okay. Then, just because this is, well, so like this part, I normally would not write it. I'm going to write it just to make sure everybody follows me here. When you do this, you're going to get plus 2 square root of x minus 1. But then whenever you do this step, you get minus 2 square root of x minus 1. And then the last term is going to be a negative 4. Now, normally, I would not write these two middle steps right here because they cancel each other out. But you can there. Don't multiply the denominator together. Make sure you keep square roots and parentheses around it. Because you want it to cancel. Alright, so if I've got x minus 1 minus 4, what does that give me when I put that together? X minus 5. So limit as x approaches 5 of x minus 5 over x minus 5 square root of x minus 1 plus 2. The x minus 5s will cancel, leaving us just a 1 there in the top. And I'm going to go ahead and plug in my 5. Once you plug in your 5, you can drop limit notation. So I got 1 over square root of 4 plus 2, which is 2 plus 2, which will give us 1/4 there. This is particularly helpful when you need an exact answer, because if you're doing this numerically or with the graph, it's sometimes hard to see that it's going to be 1/4. It might look like it's going to be 1, or it might look like it's going to be 0 or something like that. Okay, questions? Alright, I'm going to skip 10 because I'm going to make sure I have time for the other stuff first. I might come back to 10, or I may just decide to continue to skip 10. Okay, so piecewise functions. Typically, piecewise functions are going to be made up of simple types of equations. So here we have just a constant horizontal line at 5. We've got a linear equation, and we've got a quadratic. Those are our 3 simple sections. All 3 of those are continuous everywhere. Our only possibility of not being continuous, of having an interesting point in the graph, is if it happens at these places where we break. So it's going to be at -2 or at 5. So if we look at the graph for this real quick, if I graph this over here, I'm going to enter this as 3 different equations just because it's easier. It won't put the dots there, but now, these you'll be asked to do without a calculator, so you won't be able to type this into Desmos to tell what's going on. But if we look at our graph here, we have got a horizontal line, we've got a piece of a slanted line, and then we've got part of a quadratic here. It appears, just from the graph, that these are going to meet right here. Does not look like that's going to happen at x equals 5, right? So if we are looking at, this is going to ask us several different things here. If we are looking at the limit as x approaches -2 from the right. So from the right, looking at that Desmos graph, from the right side, let me type in x equals -2 so we see where we're approaching. We are on this equation, the 5, right? So from, oh no, we're not. That's from the right. From the right, not other right. From the right, we're on this graph, the red graph here, right? So -3x minus 1 is that equation. So you're going to use direct substitution. If direct substitution works. Now, notice we don't have an or equal to sign here, but as we approach from the right, we're on this. That's our right-hand function, because our split at x equals -2 is right here between these 2 functions. So we're just going to do direct substitution. We'll get -3 times -2 minus 1, which is going to give us 6 minus 1, which gives us 5. That's your y value. Yeah. Now, I only used this function because it was asking me only to go from the right. If it asked me for the limit as x approaches 5 from the right, so we split x equals 5 right here between the middle and bottom function. If it asks for the right, which function should I use, the middle or the bottom? The bottom one is going to be to the right of 5, where x is greater than 5. So we're just going to direct substitution this one as well. -5 squared plus 4. So that's -25 plus 4, which is going to give us -21. Okay. At 4, where does 4 fall? Which equation should I use, top, middle, or bottom for 4? That middle, because it's right in the middle of that, right? This should be continuous. So we're just going to use direct substitution here. Negative 3 times 4 minus 1 is going to give us negative 12 minus 1, which is going to give us negative 13. You don't get asked those questions a lot, the ones that fall perfectly, like fall inside of the ranges, but if you do, you just plug that number in there. Most of the time, though, they're going to ask you about negative 2 or positive 5 because those are the interesting points of the graph. So if they ask me about the limit as x approaches 5 of f of x, okay, I've already found the limit as x approaches 5 from the right. In order to find the limit as x approaches 5, I need to know both sides. So I need to know the limit as x approaches 5 from the right, which I already have, and the limit as x approaches 5 from the left, which I don't know yet. So limit as x approaches 5 from the left of f of x. Okay, so x approaching 5 from the left, which function should I use here, top, middle, or bottom? Middle. So I'm going to have negative 3 times 5 minus, times 5. Good gracious, what's it doing? Times 5 minus 1. That is going to be negative 15 minus 1, which will be negative 16. Now that's from the left. What was my limit from the right? Negative 21. Do those match? No. So that would mean the limit from both sides does not exist. The limit does not exist. So whenever you're doing limits, it does not matter which one is a or equal to and which one is just a less than. It's which one is on the right side or which one's on the left is what you're looking at for that. They also ask us about the limit as x approaches negative 2 of f of x. So the limit as x approaches negative 2 of f of x, we already found the limit from the right was 5. The limit from the left is going to use that top function. What's the limit from the left going to be? If I have limit as x approaches negative 2 of from the left of f of x, the function we're using is just 5. What do I get when I plug in negative 2? Any ideas? Can I plug in negative 2? I mean, is there anywhere to put that negative 2? There's not, because there's no x, right? But that just means the answer is always 5 for that function, because you don't have anywhere to plug that in. A lot of times students will do like 5 times negative 2 just because they want to put that somewhere. But if you have a constant number, it would not matter if we were doing the limit as x approaches negative 10 or negative 8 or negative 4 or negative 2 from the left. You would get 5 for any of those. So since this is 5 and our limit as x approaches negative 2 from the right was also 5, then that means our limit at negative 2 is 5. Does that make sense? So whenever you're doing the limits of piecewise functions, you're checking those two functions that come together there if it's from both sides. And since limit at negative 2 does exist, because these two give us the same value when we plug in negative 2. But the limit at 5 does not, because these bottom two do not give us the same value when we plug in 5. Alright, last thing, I think. Yeah, last thing, complex fractions. Alright, so these are fun right here. Everybody loves fractions inside of fractions. So there's some different ways you can deal with this. But in general, you just need to get rid of the complex fractions in some way. What I prefer to do is to get a common denominator up here in the top, and then you can flip and multiply after that. So if I want to get a common denominator here, I would need to multiply my x plus 2 by 2 on top and bottom. And the second fraction would need an x plus 2. So this kind of pulls back in some of that stuff that we were doing with rational equations, some of those same methods. So that's going to give us 2 minus x minus 2, because right here, make sure you're taking that negative 1. You got to distribute it to the x and also to the 2. So that'll be a negative 2 right there. Over 2 times x plus 2 all over x. You may want to keep a separate set of parentheses around that numerator. And then right here, this positive 2 and this negative 2 are going to cancel each other out. So that leaves you with negative x over 2 times x plus 2. I would not multiply that denominator back together. And I'm going to make the denominator here x over 1. Now, at this point, dividing fractions is easy as pie. You're going to flip the second and multiply. So it's going to be the limit as x approaches 0 of negative x over 2 times x plus 2 times 1 over x. And since this is multiplied here, you can cancel this x with this x. Do make sure the negative stays. So that is going to give us limit as x approaches 0 of negative 1 over 2 times x plus 2, which is going to be negative 1 over 2 times 0 plus 2, because we're taking that 0 now and plugging it in, and that will be negative 1/4. Answer. Okay, questions? I think we're just going to still skip 10. That way you can start to look at your assignment.